Okay, but let me just mention, as this is the first in a series of lectures or a series of symposia, and the next bunch of them are going to be drought in California, disaster and opportunity, vanishing beaches, water, health, and development. So these are what you might call treating water from a macroscopic perspective. I'm going to treat it from a molecular perspective. Okay, so now look, I know this is a very mixed audience. Some of you are chemists and physicists. You'll be very familiar with a lot of this stuff. Some of you are English majors or historians or people from other parts of the community. And so this talk is supposed to challenge you but bring everybody along, we hope. So excuse me for some of it may be too simplistic, and also excuse me for some of it may be too complex. Okay, so water is a very small molecule. It's H2O. What this means is it's got one oxygen, two hydrogens. We can draw the chemical structure like this, and this just shows sort of the connectivity of the atoms, hydrogen, oxygen, hydrogen, and gives you some idea of the angle that is formed. That's not a really very good picture of molecule. It's a diagram to show you what's going on. This is a better illustration of what a water molecule looks like. This is called a space-filling model. But you have to realize that you can't really draw a molecule on PowerPoint or anything else because molecules are these diffuse entities. They're really, in some sense, involve, and I'm going to talk about this a little bit more, charge density clouds. There's electrical, particularly electrons, which are these diffuse clouds. And in a picture like this, what it's trying to do is capture where most of the electrons are. But it keeps extending out. There aren't sharp boundaries. Okay, so what I want to start out with is to, just sort of, how should I say it, impress you on how weird water is. So look, here's water, which is H2O. Here's methane, which is natural gas, which is CH4. Okay, they're about the same size. They have almost the identical molecular weight in, atomic units. Water weighs 18. Methane weighs 16. As I said, they're about the same size, but they're wildly different. So if you look at this, here's the melting point and boiling point. Of course, the melting point is where ice turns into liquid water. The boiling point is where liquid water turns into steam. And look at the difference between these two things, which are almost the same size. And so if you look at this, the boiling point of water is 212 degrees Fahrenheit, or 100 degrees C. It's minus 258 degrees Fahrenheit for the boiling point of methane. Now, this is 470 degrees different. They are almost the same size. They almost weigh exactly the same amount. So why is water so different? Natural gas is a gas. It's natural gas. It's a gas. In fact, when they want to ship natural gas, you have to have these gas liquefaction plants to bring it down so cold that you get down to there so that you have a liquid. Water, of course, is a liquid at room temperature. Okay, so when we talk about atoms, you've got a very small nucleus in the middle, and if I were to draw this to scale, it wouldn't be 1 pixel on the screen. It would be much smaller than that. So this is exaggerated. But surrounding the nucleus, which is positively charged, is this cloud of electrons. And I'm trying to make it look sort of diffuse here because you should think of it more like a cloud of electrons or a wave of electrons rather than some solid object. And so, when you look at these things, an atom always has the same number of positive and negative charges. So, +1, -1, carbon, +6, -6, and so forth. But the thing about atoms is while an atom is neutral, and you can make a molecule which is also neutral, meaning there's no net charge on it, different atoms have different attractions for electrons. So when you make a molecule because these atoms and their electron clouds combine to form what we call chemical bonds. And those chemical bonds hold the atoms together. The thing about this is that they don't necessarily equally share the electrons. And so it's a very big deal that oxygen attracts electrons more than hydrogen does. Carbon attracts electrons about the same as hydrogen does. So what that means is when I look at this water molecule and this methane molecule, what we can do is assign partial charges. Now remember, as atoms, there were no charges on these things. But oxygen likes the electron so much that it drags some of the electrons away from the hydrogens, making the oxygen slightly negative, has slight negative charge, and the hydrogens have slight positive charges. In methane, this is not the case. Hydrogen and carbon have almost the same attraction for electrons. So when you have a methane, you don't have this partial, let's say, negative charge and positive charge that you do in water. And this thing right there is what makes water what it is. So these partial charges lead to very strong intermolecular interactions among water molecules. They're called hydrogen bonds. These guys have very, very, very weak intermolecular interactions. One methane molecule barely attracts another methane molecule. But water molecules really attract each other. And this is a cartoon. I'm going to show you this better. And the reason why that is look, here's one of these water molecules. This negative, slightly negative oxygen attracts this slightly positive hydrogen. This slightly positive hydrogen is attracted by this slightly negative oxygen. And the net result is that each of these water molecules, this is going to be three-dimensional, I'll show you in a second. I drew it in 2 dimensions so I could draw it. But what this does is it makes a network of water molecules. Each water molecule makes 4 hydrogen bonds. So these 2 hydrogens are, in some sense, bonded to these oxygens, and these 2 hydrogens are bonded to this oxygen. And this just goes on, and you get this network where approximately each water molecule makes 4 hydrogen bonds. These are quite strong. They're not as strong as a true chemical bond, which is important because it allows water molecules to move around, but they're very, very, very strong compared to the type of interactions you have between or among methane molecules. Here's a better look at what a cluster of water molecules would really look like now in 3 dimensions. And what you see is the water molecules, and you can see making hydrogen bonds. And the ideal structure of water, I mean, what it in principle would be is tetrahedral. Each water molecule would make 4 hydrogen bonds, and the other 4 water molecules around the center one would be in a tetrahedral arrangement. This isn't perfect, and the thing is, we have heat, and water molecules are constantly moving. Now, in order for you to boil, for water to turn into steam, for water to go from the liquid phase to gas phase, what you have to do is overcome these bonds. And these are pretty strong bonds, and that's why water boils at such a high temperature. So the strong attraction among water molecules requires a lot of thermal energy, heat, to get these molecules to be jumping around, moving with this thermal energy. And if it's moving fast enough at high enough temperature, 100 degrees C, 212 Fahrenheit, they'll start jumping out of liquid water and become a gas. Okay, so this thermal energy causes these water molecules to constantly be moving. They're breaking and making hydrogen bonds. So this is not a static structure. And the fact that, one, you have strong attractions which holds the water molecules together, but they're not so strong that at sort of normal temperatures like room temperatures, these hydrogen bonds can be broken and the water molecules can rearrange. This is what makes water capable of doing all of the things it does from geology to biology. Okay, so I'm going to show you, I said water molecules move, so this is a movie. It's what's called a molecular dynamics simulation. This was made for me by my friend Damian Laga. Actually, for this talk, I needed a movie. And I'm going to show you this. So what a molecular dynamics simulation is actually quite a high-level calculation. You do quantum mechanical calculations to figure out the interactions among the water molecules, and then you do all of these really sophisticated classical mechanical calculations to show how the water molecules move. And when I say they're all moving, what I'm going to show you is this is a bunch of picoseconds. So there. So this is more what water is doing. It's sort of hard in this movie to be able to see the hydrogen bonds being made and broken. So I've got another one here. And this one is a little different because it's designed to let you see the hydrogen bonds being made and broken. Okay, so to do that, this is a space-filling model. All these water molecules are the same. But this is the central one we're sort of focusing on. If you have this type of water molecule, if it looks like this, it's hydrogen bonded to this central water molecule. This guy over here is a water molecule getting close, and soon it will hydrogen bond as one of these other ones go away. And all of these little V guys are other water molecules, and if they get close, one of these will turn into one of those, and then when it actually makes a hydrogen bond, it'll look like this. So this allows you to actually see the hydrogen bonds being made and broken. So what I'm going to do is show you, it's going to start out not normally, and this is again a bunch of picoseconds. I'll talk about picoseconds more in a little bit. What you're going to see when I first start this is there are only going to be 3 hydrogen bonds. Normally, water has 4 hydrogen bonded water molecules. Then you'll see another one come in, make the 4th hydrogen bond, and then you'll start to see water molecules leave and other water molecules come in, and constantly rearranging this hydrogen bond network. Okay, so here's the 3 hydrogen bonds. Watch right here. Okay, here comes one. So this is what you normally have, 4 hydrogen bonds. It's all moving around. You're going to see a guy come in right here in a second. There. Okay, see, here it comes. It's coming closer. So that made, and you see that one left. So you still have 4 hydrogen. This guy went away. Here's a new guy coming in. This guy came back. Okay, so the net result is this is sort of lets you see how water is constantly making and breaking hydrogen bonds. These are strong interactions, but compared to heat, thermal energy at room temperature, they're not so strong that they can't constantly be rearranging and reforming. Okay, so we can actually measure stuff like I just showed you. In those molecular dynamics simulations, we've actually worked with these people to see that they actually are accurate. We do certain kinds of experiments, and then the molecular dynamics simulations can try and reproduce our experimental results, and then you can tell whether you've got an accurate description, which allows you to make these nice movies and see what's going on, which of course you can't see with your eye. So I said, here's water. You've got chemical bonds. You can think of chemical bonds like springs. This distance is not exactly static. So think of the chemical bond like 2 masses held together by a spring. Okay, they're held together, but classically, I'm being very classical here, you can think of these things, as opposed to quantum mechanical correct description, you can think of these things as vibrating. Now, we're going to use the vibrations as a probe, a way of looking at the water molecules. But to make it simpler, you see there's 2 hydrogens on this oxygen, so there's actually 2 things on any one water molecule that can be moving. So what we do is we replace one of the hydrogens with a deuterium. A deuterium, is like heavy hydrogen. It's just hydrogen with an extra neutron, so it has exactly the same charge. It fundamentally is almost identical to hydrogen. So it doesn't change the properties of this thing, which is called HOD. It's a hydrogen, oxygen, deuterium. But it allows us to put a little bit of this in regular water and then look at this vibrational motion as a probe of dynamics. You'll see how we do this. So classically, like I was saying, ball and spring, this guy can vibrate. So in a classical picture, you can take a pendulum, think of that as an oscillator, a vibration, and I can make it swing just a little bit, or I can make it swing a lot. And the bigger the swinging, the more energy, kinetic energies and things, it's continuous. But classical mechanics, in which energy is continuous, does not describe molecular systems. You have to use quantum mechanics. So in quantum mechanics, you have vibrations, but what you have is a state, a quantum state, in which the molecule is not vibrating, and then you can have a state where the molecule is vibrating in some sense at a certain amplitude, but you can't have anything in between. This is higher energy than this. You can have this energy, or you can have this energy. This energy difference is the difference between the lowest quantum level of this vibrational motion and the first excited or energetic motion of this vibration. Okay, so this is delta E, and that energy is related through this formula made famous by Planck and Einstein, where this energy is h nu. This is a constant called Planck's constant times the frequency. So there's only one frequency of light that will allow you to excite this vibrational oscillator. Okay, so it's not classical, it's quantized. And quantum mechanics comes up whenever you talk about molecules. For those of you who are interested in learning more about quantum theory without getting bogged down in a lot of math, I wrote this book called Absolutely Small, How Quantum Theory Explains Our Everyday World. And this is a book that is a rigorous quantum mechanics book, but with virtually zero mathematics, so you get the concepts without being lost in the math. Okay, so we're going to do experiments, and what we want to do is be able to look at all those water motions. We have a bunch of tricks. I'm going to show you one way we do this, and it involves using those vibrational motion of the water molecule. Actually, it's going to be the OD stretch of HOD. So this is supposed to be a light wave, and so it's a sinusoidal wave, and the way you should think about it is an oscillating electric field. And what it does is, so the field is plus minus, and then it's minus plus, then it's plus minus, minus plus, and so forth. Okay, so now I've got there's the other hydrogen sticking out here. I just didn't draw it. So now I've got this guy. Remember, this is slightly positive and this is slightly negative. When this positive and this is positive, they repel. This negative repels this negative, and that compresses the spring. And then half a cycle later, this is positive and this is negative. So this positive is attracted to the negative is attracted to the positive, and that stretches the spring. So the net result is the oscillating electric field of light can couple to this vibration and make it oscillate, except only if it's the right frequency. So you need to have this frequency of the light match this quantum transition, and then what you can do is you can put energy into these vibrational motions of this water molecule. So you can shine light on this thing, has to be the right frequency, this is in the infrared, and you will take the molecule from not vibrating to vibrating. Okay, so here's the big deal. When you're down here and the molecule isn't vibrating, and you shine some light on this thing, it can absorb some of the light and start vibrating. Now, once it's up here, this particular molecule has already absorbed that light, so it doesn't absorb any more light. So when you shine light on a bunch of water molecules and you put a bunch of them in these vibrationally excited states where they're vibrating, then if you shine some subsequent light on that thing, the water wouldn't absorb as much of it because you've already taken some molecules which are in the low energy state where they can absorb light and put it in this higher energy state where they don't absorb light. So excited molecules do not absorb light of this frequency, and so we can excite these things. Now, after a while, through something equivalent to friction, this will go back down to the ground state and release the energy as heat, and it'll heat the system up. But while it's excited, you've reduced the absorption of your water sample because you've excited a bunch of these molecules. Okay, so I want to look at this hydrogen bond rearrangement. And what I want to show you is because water really wants to make these 4 hydrogen bonds in a tetrahedral arrangement. Yes, they can break and rearrange, but on average, any one water molecule wants to make 4 hydrogen bonds. If I break a hydrogen bond, it really doesn't like to be dangling. So what happens is these guys are going to flip around. So rather than just sort of moving to some arbitrary position, when these guys are going to rearrange, it's not like just one water molecule breaks a hydrogen bond and then it doesn't have one. It breaks its hydrogen bond, makes another hydrogen bond. And of course, to make another hydrogen bond, that hydrogen bond had to be broken and go someplace else. So this is a cartoon, of course, and the idea is, okay, this is supposed to work. Okay, there. Okay, wait. Okay, so the idea is you get this hydrogen bond rearrangement, and if you look over here, you see this guy is making a hydrogen bond, and now it's going to go over there. And fine. Okay, my Turner is not working very well. Okay, so I showed you those movies. I didn't really tell you the exact time scale. The time scale of those motions you were seeing were a bunch of picoseconds. I'll come back and define that better. But so we want to look at these water motions. So we have to be able to do an experiment that's fast. We have to have a system like, camera with a shutter speed that's much faster than the timescale of the motions. So we can make infrared pulses of light, and these pulses of light are tunable. So we can tune the frequency to match that vibrational excitation transition. And so we can tune that, and we can make pulses that are 60 femtoseconds long. So let's just say what that is. A femtosecond is 10 to the minus 15 seconds. So this is 1 femtosecond with all those zeros. So a femtosecond is a millionth of a billionth of a second. It's really a short time. Okay, and we can make this is very, very short. We can make pulses of light that are 60 femtoseconds long. We can tune them to the right frequency to excite that OD stretch of that water, that deuterated water molecule. So here's our sample. And what we do, we have lots of laser equipment over here that makes this very fast, tunable IR pulse. It's going to come into the sample. So when this pulse of light, this very short pulse of light passes through the sample, it's tuned to the right frequency. So it's going to take some of those water molecules, those HODs, and it's going to get that OD stretch vibrating, putting it in that n equals 1 first excited state. And the big deal is, once it's in that first excited state, any subsequent light coming in that's at the right frequency, that molecule won't absorb it anymore because it's already up there. So it absorbs the light by going from a lower energy state to a higher energy state, so it's not going to absorb it anymore. So this thing is going to take some of these molecules and take them from here to here. Okay, so then what we do is we bring in another pulse of light. And we bring it in a known time later. We can control this time t. This is called the probe pulse. This is called the pump pulse because it pumps the molecules up into the excited state. And then we bring in a weak probe pulse to see what's happened. And because this pump pulse went into the excited state, put some of these guys in the excited state, more of this probe pulse will make it through the sample to my detector than if I didn't have this. So if I didn't have this thing, then a lot of this would be absorbed and I get some signal. But when I put this in first, it puts these molecules in the excited state, so less of this is absorbed. And the signal is change this time and do experiments that are related to how much of this guy is absorbed depending on time, and I'll get back to it later, and polarization after you've put in this pump pulse. Okay, this is what we call bleaches the sample. When you excite this thing with the pump pulse, you put a bunch of these molecules in the excited state, the sample is bleached, and what that means is it's more transparent to subsequent light of this frequency, delta equals h nu coming through. Okay, so first I want to show you an experiment we can do where by playing certain games, I want to measure rotation. And the reason why I want to measure how the molecules rotate, as I showed you, to rotate, you have to break and make hydrogen bonds. So if you measure the time of rotation, you're actually measuring the time for breaking and making hydrogen bonds. So you get that information about hydrogen bond dynamics. Okay, so as I said before, when you pump this stuff up, it doesn't stay there forever. It's like if you have a pendulum on a clock, but you don't keep kicking the pendulum, friction will eventually make the pendulum stop moving. There's the equivalent of quantum mechanical friction, which causes this thing to go from this excited state back down to this low energy state, and the energy has to be conserved. It comes out as heat. Okay, so we can measure this time, how long after I get one of these molecules vibrating, how long does it stay vibrating? And we do it with this pump probe experiment. We put some in the excited state, and then we look after a time t, the transmission of the probe. And as we make t longer and longer, in other words, we bring this in later and later, more of these guys will have gone back to the low energy state, which they're absorbing again, which means more of this will be absorbed. So as you increase this time t, less and less of this makes it through the sample, and you get a signal that looks like this. Okay, so this is a scan of this time t. You start with the two pulses on top of each other, and you get a signal, call it 1, and then as you scan this that way in time, meaning longer and longer time, you get a decay. This decay is showing you that less and less of the light is making it through the sample, and from that, from the time dependence of that, we determine the time that molecules stay. Once you've put them in this vibrational state, we can measure how long they stay there before they turn that energy into heat, and that's 1.8 picoseconds. So again, a picosecond is a trillionth of a second, and just to get a feel for how fast that is, 1 picosecond is to a second as 1 second is to 32,000 years. Okay, so just to give you a feel that a picosecond is very fast. Since we have femtosecond timescale pulses, which is 1,000 times shorter, we can easily measure this timescale. Okay, but what I want to tell you, and this is where you're going to have to work with me and think, this is where the work starts, how we can measure rotations with this type of measurement or something similar. Okay, so look, here's my OD stretching mode that I want to excite. I'm calling this vertical polarization. The electric field has a direction. I can make the electric field oscillate this way. I can make the electric field oscillate this way by just manipulating what's called the polarization of the light coming in. And okay, so remember I said if it's oscillating like this, remember it's going plus, minus, plus, minus, plus, minus, and it's that coupling to the oscillating field plus, minus, that drives this thing. However, if I change this to horizontal polarization, then the molecule is like this, plus, minus, but the plus and minus of the electric field is going that way. This guy doesn't care that it's doing that. It needs to be driven like this. Putting the oscillating light this way will not excite the thing. And the same thing goes this way. I mean, if the molecule is sitting like this, remember there's another hydrogen over there, it's a water molecule. If the thing is sitting like this, vertical polarization won't excite that. You have to have the electric field oscillating along the bond in order to couple those plus minus partial charges to the plus minus oscillating electric field. Okay, so this is going to give us a handle, you'll see, on measuring rotations. So again, we're going to do this same thing I just told you, except we're going to play games where we're going to look both with the probe pulse parallel in polarization to the pump pulse. So if the pump pulse is vertical, we can make the probe pulse vertical. But if the pump pulse is vertical, we can also make the probe pulse have its electric field oscillating horizontally. Okay, so for molecules with this orientation, the pump will excite it, and the parallel probe will know it's excited because more light of this, the probe, more probe will go through. But if I excite this thing with the pump and I put the probe this way, then it doesn't care that I've excited this because this wasn't going to be absorbed by molecules that are pointing that way anyway. So when the pump and probe are perpendicular, you excite molecules with the pump, but with the probe perpendicular, you're not going to get, even though this was absorbed, this polarization doesn't see the so-called bleaching and more transmission. So that's going to give us a handle on measuring the rotation. Okay, so what we're going to do is we're going to do two kinds of experiments. We're going to put in this pump vertically, and then we measure the time dependence with the probe either vertical or horizontal. Okay, so if I have this orientation, this will excite this bond, and if I have a parallel probe, I'll get a signal, but if I have a perpendicular probe, I won't get a signal because I'm exciting this way, and this guy wouldn't have been absorbed by this molecule anyway. Now, this orientation will not be excited by the vertical pump, right, because it's pointing this way, and this is oscillating this way. I need it to oscillate that way. So it won't excite this vibration. And so there'll be no signal for parallel or perpendicular probe because I just didn't excite the molecule. So you can see there's a difference depending on how the molecule is oriented, and it's going to rotate, so it's going to change its orientation. There's a difference in what vertical pump and vertical and horizontal probe will do depending on which way the molecule is pointing, and that's our handle on measuring rotation. Okay, so here's the bit. I excite this molecule. It's excited. It's parallel, and now it's going to rotate and become perpendicular. So it makes a signal for the perpendicular probe when there was none at t equals 0. So initially, when I was looking in this direction, there were no excited molecules this way, but this excited molecule rotated over there. Now it's vibrating this way, and my perpendicular probe, which right at short time before a molecule had a chance to rotate, there was no signal. This will actually cause a signal to grow in. You'll get a signal. And same thing happens this. Let's say I had this molecule. It wasn't excited initially because I have this vertical pump, but if it rotates, so this unexcited molecule now is pointing vertically, the vertical probe now sees more molecules that aren't excited to absorb, so that's going to cause that signal to be reduced. So the whole point here is you can see how if the molecule rotates and we look with, let's say, vertical pump and then vertical and horizontal probe, you're going to get different signals, and their time dependencies are going to depend on the molecules rotating. Okay, so here it is. So you make these two measurements, and you combine the data with a well-known formula, and here's what you get. So what this is, the blue stuff is the data, the dashed line is an exponential fit, and what you get is 2.6 picoseconds. So this 2.6 picoseconds is the time for hydrogen molecules to rotate. But remember, for them to rotate, this guy is hydrogen bonded. If this guy is going to rotate, it doesn't just go anyplace. It's got to make a new hydrogen bond. And if it's going to make a hydrogen bond to this water molecule, whatever was making that hydrogen bond had to flip out over there and make another hydrogen bond somewhere else. So this is what's called a concerted process. It involves many water molecules, and rotation really depends on the rearrangements of hydrogen bonds. So what you can see is water can rearrange its hydrogen bonds very, very rapidly. Okay, and that's this idea that the rotation is hydrogen bond rearrangement. Okay, so why do I care about any of this? There are countless processes in nature and in technology that depend on this. We wouldn't be sitting here talking without hydrogen bond rearrangements. Nothing in your body would work without those water hydrogen bond rearrangements. Here's a simple example of just hydrogen bonding. So salt crystals, sodium chloride, table salt. What holds it together? You've got positively charged sodium ions, negatively charged chloride ions. They attract each other. They arrange in a way that these positive and negative charges strongly attract and make this sodium chloride table salt crystal. Why can water dissolve something like this really nice crystal? Because water has this type of structure where you've got the slightly negative oxygen and the slightly positive hydrogens. So for the sodium, which is a +1 charged ion, it gets surrounded by water molecules in such a way that the negative part of the oxygen points at it. But for the negative ion, the chloride, the water arranges so that the positive parts point at it. So in both cases, the positive ion and the negative ion are happy in water because water has this positive and negative attributes to it. And for that crystal to dissolve, water is at the surface and it's rearranging as a ion comes off because of attraction to the water rearranges and forms this type of, I've drawn this in 2 dimensions, this is really 3-dimensional structures, forms this type of solvation shell that can dissolve these things. Okay, more clearly dynamical in nature is, your body, most of the functions in your body are carried out by proteins. And proteins are these long strings of amino acids, and they're made by this thing called the ribosome, which is this chemical factory, and it spits out this chain of a certain order of amino acids. But when it comes out just like this piece of spaghetti. But your proteins, to function in your body, have a particular 3-dimensional structure. This is going to fold into that. That's an alpha helix. That's what's called a beta sheet. The point is, this thing has to get, after it comes out of the ribosome as just this piece of spaghetti, it has to get into this complicated three-dimensional shape. And one of the principal things that drives it is hydrogen bonding with water and the ability for it to rearrange what's called protein folding and form the right shape is because water can rapidly rearrange its hydrogen bond structure to accommodate this. So what you've got is amino acids, some of which are polar. In other words, they are charged or have positive or slightly negative charges. They like water. Some of it they are nonpolar. They hate water. And so this thing tends to form into a structure that puts the polar amino acids interacting with water and buries the nonpolar amino acids inside. And this is one of the major driving forces of protein folding. And it can happen because as this thing is getting into the configuration, water can rapidly rearrange its hydrogen bond network to keep accommodating each new configuration as this thing folds up. So these are just two examples, but I mean, water and its hydrogen bonding is everywhere. Okay, now, in this protein thing I just mentioned, and in general, I first talked about bulk water. Water, in just so many instances, in fact, I probably set it up here maybe a little too much, but almost everything that's important, you don't have just pure bulk water. You got water with ions in it. You got water in your biological systems. I'll show you some more pictures. You've got, so here's one of them, which is a water channel through a protein. You've got things like fuel cell membranes. You've got a hydrogen and oxygen fuel cell. You've got to separate the oxygen gas from the hydrogen gas by a membrane. The thing is, when you take an electron off of a hydrogen, you've got to get electrons out, it's a fuel cell, that's what you want, you end up with a proton, a positively charged hydrogen. Eventually, that has to get and meet up with these oxygens to make water, which is why we like hydrogen-oxygen fuel cells, because the waste product is water. So out of your tailpipe would come water if you had a hydrogen-oxygen fuel cell. And to do that, protons have to move from one side to the other, and they do that by having these nanoscopic channels, a couple nanometers in diameter. A hair is 100,000 nanometers, okay? A couple of nanometers in diameter filled with water, and protons can move through this, but hydrogen and oxygen can't. So these are like membranes in your cells. Your cell membranes are solvated by water molecules. So there's many, many instances where you don't have pure bulk water, but you have water interacting with interfaces, also in confinement, where you only have a very small number of water molecules on very small distance scales. Okay, so water is the medium of life. I've sort of been saying this. There's just so many ways that water comes into your biology. You've probably heard that you're 65% water. It's not bulk water. It's things like this. This one is aquaporin. I just grabbed these things off the web. Notice how they drew their water molecule with my partial charges. This is a water channel. These are ion channels. This is potassium chloride water channel. So this is a big protein. This is sort of a channel through it. This is the potassium. This is the chloride, and this thing moves through, and you can see there aren't a lot of water molecules here. Clusters of water molecules inhabit these channels and various other parts of proteins. So when you're dealing with many, many systems, whether it's a man-made fuel cell membrane or an ion channel in biology, you're not dealing with bulk water, you're dealing with confined water, clusters of water molecules interacting with interfaces. So we've studied this a lot, and what I want to do is show you one example of a really nice system where we can study water interacting with interfaces and also very small numbers of water molecules. Okay, so I have to tell you what this is. I'm going to tell you about what are called reverse micelles, but first I got to tell you what a reverse micelle is. This is what's called a surfactant. It's a soap molecule. Okay, these guys are just hydrogen and carbons. This is oil, right? This is just a chain of oil. This is a nitrogen. This has a positive charge over here. So this part of the molecule is positively charged, and it likes water. So this is like oil. It hates water, okay? So what happens when you wash your hand? You've got grease or oil on your hand, and what happens is the oil part of this molecule goes into the grease and sticks in there. The head group here, what is called, which is positively charged, hates the grease. It sticks out into the water, and that solubilizes it. You now have this grease which likes the water because it's got all this stuff pouring out of it that can be dissolved in water, and that causes the grease to come off your hands, and that's how soap works. Okay. When you wash your hands, there's a small amount of oil and a lot of water. We can do this thing make a reverse micelle, which allows us to make little balls of water by sort of reversing this. If you have lots of oil and only a tiny bit of water, the water hates the oil, hydrocarbon, and these soap-like molecules, the oil part of the soap-like molecule wants to be in the oil. The head group, which are charged, these types of things, they want to be in the water, and the net result is this thing forms into this structure called a reverse micelle. A micelle has the charged part sticking out, and you can make these little balls of water. And this gives us the opportunity to study a small number of water molecules, as well as being able to look at water interacting with interfaces and so forth in a controlled manner. Okay, so here is the picture again. Starting to, excuse me one second. Okay, maybe. So this is this molecule that makes this thing up. It's called AOT. It looks like this. Okay, so here's the trick. Just by changing the ratio of the number, oh, now I'm going to have two non-working laser pointers. The number of water molecules to the number of surfactant soap molecules, you can change the size of this ball of water. So this is this parameter W naught. So it can be two water molecules per surfactant, or like 46, and you can go from like 40 water molecules to 150,000 water molecules in a very controlled fashion. So what you can do is you can make the number of water molecules and this little pool of water get bigger and bigger and bigger, and this is our handle on being able to study what happens when water interacts with the interface, that's those guys, and also just what happens when you have just a really small number of water molecules confined into a very, very small space, like this is maybe, 2 nanometers across here. Okay, so first I just want to show you what happens when we look at what we call large reverse micelles. So you've got, the organic phase, and then you've got the surfactant tails. This is the water. And when it's what I call large reverse micelle, it's because the water is divided into two types of water. There's water right at the interface. That's going to be really different from bulk water. But if you make this thing big enough, the water right in the middle or away from the interface is going to look like bulk water. So for a so-called large, what we've defined as a large reverse micelle, means it's big enough that you've got a pool of water in the middle that's just like bulk water, but when you get near the interface, because it's near the interface, it's going to be that's what I'm going to show you, it's going to be very different from bulk water. Now remember, in bulk water, the rotation time is 2.6 picoseconds. That's what's going to be going on in this region. And what we want to do is see what's happening when you've got water molecules up against an interface. Okay, so we can do that same experiment I told you about before, this polarization-dependent pump probe experiment. And here's my water data again, 2.6 picoseconds. And you can see that this looks very, very different. This is W naught equals 25. It's one of those larger ones, so there's a pool of water. And by analyzing this with the right equations, you find that it's got two components. One looks like bulk water rotation. It just gives you the 2.6. And the other part is what the water molecules are doing when they're right up against the interface. And for this one, we find that rather than 2.6 picoseconds, you find that the orientational relaxation of water molecules up against the interface is much slower. It's 18 picoseconds. And actually, we've done this for many sizes. As long as they're large, it doesn't actually change this time. It's always 18 picoseconds, because what you're looking at is water right up against this interface, and that water doesn't care how big this ball of water out here that looks like bulk water is. Okay, so what we see is as soon as you don't have pure bulk water, things slow down. And why do they slow down? Okay, here's why they slow down. So again, remember, these are really three-dimensional structures, but this is my ability to draw these things. Okay, so remember, you saw this in that simulation. Here's a central water molecule with 4 water molecules making hydrogen bonds. And you saw this. Then you'll have one of these water molecules start to get close, move in from the outside. And when it gets close enough, all of these guys flip around, and you get that concerted hydrogen bond rearrangement. But remember, to get those hydrogen bonds to rearrange, the energetically really important thing is that you don't have dangling. If this guy is going to go that way, then something's going to come over here. Whatever was over here had to flip out and make another hydrogen bond in this concerted process. What happens when you have an interface? It just blocks a lot of pathways. No water molecule can move in from here because there's no water over there. And I can't have this guy flip around to make a hydrogen bond over there because there are no water molecules there. So just having the presence of interface, and we've done this on a bunch of systems, the actual chemical nature of the interface is less important than there's just an interface. And what that interface does is disrupt the ability of these guys to make these multi-water molecule concerted rearrangements, and everything slows down. Okay, so this is for a reverse micelle when it's so big that in the middle it's bulk water-like. Okay, what happens when you get smaller? So that's the big ones. When you start getting smaller and smaller, the ball of water, you still got the stuff at the interface, but the ball of water in the middle is getting smaller and smaller because the whole ball of water is getting smaller. Okay, so why does that matter? I just sort of showed you that these water molecules right up against the interface are really, really affected by the interface, and you get tremendous slowing. But you can imagine that if these water molecules are different than bulk, it doesn't stop immediately. This is going to propagate out some distance. These are going to be less different, but they're going to be somewhat different. These are going to be even less different. And if you've got enough water, eventually it doesn't know the interface is there, and it's bulk water. It's really interesting to know what distance do you have to move away before a water over here doesn't know there's an interface over here. Okay, so what happens if there's another interface that's close enough in? Okay, these water molecules are very different, and then they're getting perturbed, and if before these guys are like bulk water, they meet these aren't like bulk water, they meet these guys that aren't like bulk water, there's just no bulk water. So we can look at these, we can make these things smaller and smaller and smaller. And remember I said with the big ones, you always get the bulk water number plus this much slower number. As you make them slower and slower and slower, the core, that sort of pool of water in the middle, it gets small enough, it starts to feel the interface, and at this size, you can start to see the change. It goes from 2.6 picoseconds to 4 picoseconds because the water in the center is slowing down. That even slows down more the water at the interface. That goes from 18 to 26. So we consider this the dividing line where the diameter of this thing is 4 nanometers. So just as, very qualitatively, you can think, you've got to move more than 2 nanometers away from an interface. You've got to have enough bulk water that if you can move more than 2 nanometers into what is bulk water, you'll have bulk water. But if the system gets small enough that, there isn't 2 nanometers away with a bunch of water over here, then none of the waters are going to look like bulk water. And of course, that comes up in biology a lot. And what happens when you make the thing really, really small? What I just described was, okay, I have an interface and I have the middle, which is starting to feel the effect that these guys are really different, somewhat different, less different, but these are now affected. But when it gets really, really small, so this is W naught equals 2 with only 40 water molecules, there's nothing that's very free. So even in that medium-sized one, you had a core, it was slower, but those guys they weren't up against the interface. They could flip around and rearrange their hydrogen bonds. They were slowed down because they were having to rearrange involving ones that were really slow with the interface. But when you get slow enough, there just aren't the pathways to get this rapid flipping around, and things really, really slow down. So here's my bulk water again, 2.6 picoseconds. And for this 40 water molecule ball of water, This thing, well, it's really, really, really slow, as you can see. It's so slow we can only give an estimate of the number. It's 100 picoseconds or longer. So in these types of systems like this, where you have clusters of water, a few tens of water molecules with this amino acid protein interface, these water molecules are not going to behave like bulk water at all. And this is one of the big frontiers in biology and chemical physics and physical chemistry. I can do these experiments on reverse Micelles, and this is informed biology of what is the nature of small water pools. But a thing that we would really like to do, and we hope to be able to do it, but the biology is tricky to get a system you can try it on, is to actually look in a real protein channel, what are the nature of these water molecules? Because it's known, not how, but water is essential for moving ions and other species from outside of a cell, inside of a cell, and from inside the cell, outside of a cell. Everything is sort of carried along by a small number of water molecules that interact with the amino acid interfaces and surfaces in particular ways and help move and help part of the selectivity reject other things that you don't want to go through the interface. Okay, so the net result is that when you get very, very small, things are very, very different from bulk water. And this is one of the big frontiers of trying to understand what we call nanoscopic water in nano confinement does, but in particular biological systems. Okay, so what I've tried to say is, water is ubiquitous in nature. It plays fundamental roles in biology, chemistry, material science, and geology. And we know a lot about water. And we know a lot about water in nanoscopic confinement. But that is really the frontier, because there are so many systems where water is of central importance, but the details of the system, the ion channels or the fuel cell membranes, each one of these has a different nature of interface, different size, different number of water molecules. Can we get enough understanding of these different kinds of systems to really, really understand water's role in these really complicated processes, and maybe get to the point where we understand enough of them that we don't have to measure every single one of them? Right now, there are no experiments like on the water in protein channels to tell you about the type of dynamics I've been talking about here. Okay, so I just want to thank you very much, and I appreciate again the invitation. If you have questions, I'm happy to answer them.